this. See, as I said, t itself, which we calculate on this plane that is defined by n, is calculated by multiplying the stress tensor with n, so you get the t. This vector t, the stress vector on this plane, it is not perpendicular to this plane. It can be at some angle, so we can calculate the normal component and the shear component of this vector here. The normal component can be found by multiplying with n again, so this projection, as I said, can always be found by multiplying with the normal direction. And then the shear component can be found through Pythagoras, so this length is the square root of this length minus the square root of the minus the square of the square of this one. So the square root or the square of this one is equal to the square of this one minus the square of this one. And then we are going to solve some examples. So example 3.2, let the component of the stress tensor at a point P to be given in this form, and the units are megapascal. Find the stress vector on the plane passing at P, and then the stress vector at another plane passing at P. You have the stress tensor to be 2130. Yeah, this is sigma 2163 negative 42 and 84 and 0, and then minus 21, and then 84 minus 63 and 42. Okay, so this is the stress tensor, 21, 63, 42 minus 21. This is the stress tensor. And we have the normal direction 1/7 multiplied with 2 minus 3 and 6. So we have a normal direction and we have a stress tensor. We are interested in finding the stress vector and the components of this stress vector. So the shear and the normal components. So to find the stress vector, I'm just going to call it T again here. So T is equal to, and this is a tensor and this is a vector, so I need to remember to write in order to draw the bar. So T is equal to sigma multiplied with n, and this is sigma is 21 minus 63, 42 minus 63, 0, 84, 42, 84, and minus 21. This is multiplied with this vector. It is 1/7, 2, minus 3, and 6. So you need to multiply these together, and then you get the vector here. I'm going to keep 1/7 outside. Oops. 2 multiplied with the 21, this is 42. Minus 63 multiplied with 3, this is plus 63 multiplied with 3. And then 42 multiplied with 6. Can someone give me the answer for that? So basically, 42 added to 63 multiplied with 3 added to 42 multiplied with 6. It's 483. Oops. 378. 94. All right, so this is the vector T. Now, if you want to calculate the normal and the shear component of T, you have to multiply T again with the normal direction. So you have T to be 1/7 483, 378, and minus 294. So in order to find the shear components, and let us assume that this is T. So in order to find the normal component of that, just use use a different color. I think it's better. So this is, I'm going to call it Tn, and this length here, I'm going to call it Ts. So to find Tn, you have to multiply T one more time with N, and you have this to be 1 over 7, 483, 3, 7, 8, 294, multiplied with the N vector again, and the N vector is here. It is 2, minus 3, and 6. One over 7. So if you multiply them together, you will get the value of Tn. If someone can multiply them and give me the answer for Tn. I just probably switch back to the board so you can write them. So it's basically 1 over 7 multiplied with 1 over 7. This is 1 over 49. And then you have, I don't need to use a square bracket, 483 multiplied with 2, minus 3 multiplied with 378, plus 6 multiplied with minus 294. So what would be the answer for that? This is the component Tn. Now, in order to be able to find Ts, you need to find the length of this vector T. So you need to find the length of this guy and do that. So in order to find Ts, you need to square this number, 39.429 squared, and this is negative, added to the length of T squared. So what is the length of T? The length of T is the square root of the sum of the squares. So basically, it is going to be the square root of the sum of the squares. So I'm just going to write down the vector itself. So this is the length of that. So this is going to be the square root of the sum of the squares. So it is 483 divided by 7 squared, added to 378 divided by 7 squared, added to minus 294 divided by 7 squared. So you need to calculate this length and put it in there. Now, because this is square, you can get rid of the square root in there. You don't have to include that in there. And you subtract the square of this number. You have the square of Ts. Once you have the square of Ts, you can find the shear component. So you can take the square root of that and you get the Ts. All right. Can someone give me Ts? Ts here. So you basically need to calculate the length of T. If you can give me the value of T first, or instead of T, I'm just going to remove the square here. I'm just going to put a square here. So that we can't put the number immediately. We can put the number in here instead of finding the square and then squaring it again. By finding the square root and squaring it again. So it is minus 39.429 squared added, okay, 9441. Calculate the square of 39.429 and subtract it from 9441. We will have a value for Ts. 354. So this is Ts squared. Can you give me the square root? 81, and this is in megapascal, and this is the answer for the shell. This is these expressions. I'm just going to summarize them below. Oops. I'll just try to summarize them here. So first of all, the stress vector is equal to the stress tensor multiplied with the normal direction for the plane you are interested in. And the second thing is, probably since we are using capital letters for T, I'm just going to call it sigma n. So the normal component, or probably Tn is equal to T multiplied again with n. So this is the same T multiplied one more time with n. And Ts squared is equal to Tn squared in negative added to the length of Tn squared. This is vector squared. Okay, so this is vector, this is vector, this is tensor, this is vector, this is vector, and these are scalars. So these are components. So this is the component. This is the component of T in the normal direction. This is the component of T in the shear direction. If you like, you can write it in this way. Or if it is easier for you to remember, this is T, and this is T. This is the length of the T, this is the normal component, and this is the shear component. Find the normal component. Do a projection. You always, if you want to find a projection, multiply with the normal direction. If you find if you want to interested in finding the stress vector, multiply with that. So this is pretty much all the discussion we had so far today. Oops. Go back to this example here. So this example is from one of the books. So the solution can be found in there in details, but I'm going to have a just short discussion on this example. This is a slightly different example. We know that the example states that the stress tensor is given by this value here, is P multiplied with I. P is a scalar number, it's just a P number, a scalar number, and I is the identity tensor, and sigma is the stress tensor. So I'm going to write down the stress tensor. So sigma is basically equal to P multiplied with the identity matrix. So the identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. So basically this is equal to P 0, 0, 0, P 0, 0, 0, and P. So this is the stress tensor. This is the stress tensor sigma. So it is negative, so we have a negative sign in there. So this would be negative, negative, and negative. Now, the question is, show that the shear stress on any plane containing this point is 0. So we have a general plane, any plane. We are going to define this general plane with this normal direction, N1, N2, and N3. So we have N for any plane, which will have general components N1, N2, and N3. We want to show that for any N, there is 0 shear components. So there's no shear components at all. So to show that, you just multiply. First of all, we need to find the stress vector on this general plane, and then we want to find the shear and the normal component of that. All right? So first of all, we want to find T. This is sigma multiplied with N. So this is minus P, 0, 0, 0 minus P, 0, and 0, 0 minus P, multiplied with N1, N2, and N3. So it is n1 multiplied with minus p plus zeros, 0 minus np, or minus p multiplied with n2, and 0 minus p multiplied with n3. So this is going to look like this. Minus p n1 minus p n2 minus p n3, or just simply minus p multiplied with n1, n2, and n3. All right, so if you look into n1, let us assume that this is n1. I'm just going to draw a coordinate system, x, and let us assume that this is just happening in 2D, just to be able to visualize it. And assume that this is n, right? This is n, this is the general n. If you look into this, you'd see that this p multiplied with n is only going to elongate or shrink n or change the direction of n, but n is always going to stay. This new vector minus p multiplied with n is always going to stay on the same line. And no matter how big or small or what value you pick for p is always going to result into a new vector. This new vector is going to always stay on the same line. So let us assume that p is going to enlarge the vector, so make it longer, but it's still staying on the same line. So if it is the case, then the new vector would also be perpendicular to the plane that we are looking at. And if it is the case, then there will be no shear component for that. So by discussion, you can see that there is zero shear component for that. But if you don't trust that, try to solve the example one more time, but this time using these equations in there. So you have found t. This is the vector t. It is minus p n1, n2, and n3. Now I want you to continue solving this example and find the normal component of that, multiply again with n, and then find the shear component of that. So the shear component will need to be 0. In this case, it's going to be 0. Now, this is going to be 0 because this new vector is lying on top of n, is perpendicular to the plane. So this is why the shear component is going to be 0. So I would give you 5 minutes. In these 5 minutes, try to find the normal component Tn and then the shear component Ts of this vector. All right, so have 5 minutes and try to solve it. It should be quite quick and straightforward. Probably then explain it a little bit further. And if you have further questions, we can discuss them again. So t is equal to minus p multiplied with n1, n2, and n3. This is t. This is the vector t. Now, if we want to find tn, this is the component, the normal component. We just multiply n1, n2, and n3 again with n1, n2, and n3. Now it is going to be minus p multiplied with n1 squared added to n2 squared added to n3 squared. All right, this is Tn. Now, because this is a normal direction, any normal direction, the length of the normal direction is going to be 1. Always for normal directions, you should pick a length equal to 1 because we are going to use this to multiply it with the stress tensor. If the length is different than 1, then in this case, it's going to scale the stress vector up or down. So the length of this n should always be 1. So the length of this vector is the square root of the sum of the squares. So the square root of the sum of the squares is n1 squared added to n2 squared added to n3 squared. The square root of this is equal to 1. So this is equal to 1. is equal to minus p. And if you are going to find the length of this vector, now we go back to t. So the length of t, which is, I think Bleak asked about that, is the, I'm going to write it in this way. Hopefully this is going to be, or probably just go get this one and find the squares of this one. So this is probably easier for you to see, Bleak. So the square root of the sum of the squares is minus p n1 squared added to p n2. I'm going to drop out the negative sign because it will go away with the square. So the length of that is going to be p squared multiplied with n1, n2, and n3 squared. Take the square root, or you just simply take p multiplied with the square root of n1, n2, n3 whole squared. So again, the length of the normal direction is equal to 1. So this is going to be equal to p. So the length of t is equal to p. And we know that ts squared is equal to tn squared minus and plus the length of t squared. So tn squared is minus p squared. This is minus p. You have negative here. And then you have the length to be p squared. So this is p squared. So this is equal to 1. All right, so we have the normal and the shear components of the stress vector. The other thing we have about the stress vector is the principal stresses. So the principal stresses and the principal stresses are the eigenvalues of the stress tensor. So if you have the stress tensor T, you calculate the eigenvalues, just the values of lambda, and these are the principal stresses. Now, these principal stresses are the maximum normal stresses this stress can attain at any plane. I'm going to explain it in a minute, but I want you to get yourself familiar with the numerical procedure, and then we can see what does this values mean. So the principal stresses are the maximum normal stresses, and these are normal stresses. These are normal values of the stress. And there is shear stresses as well. This is the maximum shear stresses, and can be calculated using this equation here. I probably show you these equations in details later on. But I would prefer to explain it first of all. I would try to explain it on the cube which we had in the beginning of the lecture, or in the beginning of this part. And then we get into the shear stresses. Okay, so probably this cube is too crowded. It is difficult to see how to draw on top of that. So I'll probably just go back to the example of a vector. So we have x1 and x2 coordinate system and a general vector v. All right, so this is a general vector v. We mentioned before, if you want to find the projection of this vector in this coordinate system, you have vx1 and vx2. These are the components of v. Now, if you decide to rotate the coordinate system, and instead of x1, x2, let us have x1 bar and x2 bar. Now, x1 bar is actually parallel to v, so it's happening, the entire length of v is projected on x1, and you have 0 component for x2. So if you write the components, I'll probably just write it again in red because this is the vector itself. Vx bar and Vx2 bar, if you write that, you'll find that this component is going to be some number, and this is going to be 0. So I'm going to call it E. Now the length of Vx1 and Vx2, or the length of V, the vector, I mean, how do you know that this is the same vector? If you calculate the length of this vector, you find the length of this vector is simply the square root of the sum of the squares. So it's going to be Vx1 squared added to Vx2 squared. If you calculate the length here, is the same vector again. Is going to be the length squared added to 0 squared, and then you have V is equal to okay. So you see now, what is happening is if you have a coordinate system x1 and x2, you have values for Vx1 and Vx2. But if you rotate the coordinate system and you have the x1 exactly parallel to the length of, or to the V1 direction or the V direction, you'll have the length of V projected entirely on x1, and there's no projection at all on the x2. It is 0 and the full length projected on x1. See that this is in 2 dimensions, and this is a vector. So it is easy to imagine that. Now I'm going to move back to the stress tensor, this stress tensor here. For a coordinate system x1, x2, and x3, this is projected into the full length or the full matrix here. Now, if you rotate the coordinate system, let us assume this is a new coordinate system. It is 3, 2, and 1, and this is in bars. These values here are all going to be changed. So these numbers will be different. But the stress tensor is still the same. So the numbers are different, the projection is different, but the stress tensor is the same. Now imagine that you keep rotating this coordinate system until you get the projection to be only that. T11, 0, 0, 0, T22, 0, 0, 0, T3, 3. Now, this is a possibility. There is a certain coordinate system that this specific coordinate system would have the stress to be projected only in the normal directions. So there is a certain coordinate system. At this coordinate system, this cube here will project the stress completely in the normal directions. So it's going to be T11, T22, and T33. So it is pure normal stress. Now, this is still the same stress tensor. It is only that the stress now is purely projected in these directions. Now, this is going to be just like in the length case, when you projected the entire length of V1 in the x1 direction, just exactly in the same situation, you have the full length projected only on one direction and the other direction is 0. What would happen here is this projection is going to be maximum in the normal direction. You see that? So this is the thing. So the maximum normal stresses would happen on this specific coordinate system, which I don't know. I mean, there will be a coordinate system. I don't know this coordinate system. But this coordinate system, if I project the stress tensor, I would only have these numbers in there. And these numbers are certainly going to be the maximum normal stresses. So this T11 in this coordinate system here is going to be certainly larger than T11 in this coordinate system, and is certainly going to be larger than T11 in this coordinate system. So this is going to be the maximum normal stresses that would ever happen because of this stress tensor. There is no way that this normal stress is going to exceed that. Just in the same way, there is no way that you will get the component of a vector to be larger than the entire length of this. So if you go back here and you want to find these maximum projections, you need to find the eigenvalues. So this is the eigenvalues and the directions of them. This direction here, the direction of them is going to be the principal direction. So this is going to be assuming that this is going to be lambda 1, this is lambda 2, and this is equal to lambda 3. So the eigenvalue is going to be equal to the maximum normal stress, and the eigendirection, so this vector here, is going to be the eigenvector of lambda 1. So this is going to be n1, this is going to be n3, and this is going to be n2. So the eigenvalue problem has a very significant meaning in the case of the stresses, because it does really impact how you are going to use these stresses in the design. So if you are going to design for normal stresses, the maximum normal is going to be T1, T2, and T3. And the direction of these stresses is going to happen in the N1, N2, and N3 directions. So the principal directions are really important, and the principal stresses are really important. Now, in this course, we are going to always organize T1, T2, and T3 in order. So we're going to have the maximum eigenvalue is going to be T1, the second largest eigenvalue is going to be T2, and the third largest eigenvalue is going to be T3. This is how we are going to, this is some sort of a convention we are going to follow in this course. All right, it's quite a popular convention that you would always have them in order, but in this course, at least for this course, we are going to stay with the eigenvalues organized so that you have the largest eigenvalue to be equal to T1, the second largest is equal to T2, the third largest is equal to T3. Okay, so this is the meaning of the eigenvalues and the eigenvectors.